Hello and welcome to week 7. Finally, there is some light at the end of the tunnel. This week we will be talking about concrete as a structural material. We will cover its basic advantages and disadvantages. We will also talk about a variety of different concrete systems, and there are many. And we will be talking about how to size basic concrete elements like columns, beams, and slabs. We will also cover briefly a variety of foundation systems and learn when each is applicable in different circumstances. So let's first start with the advantages and disadvantages of concrete as a structural material. And you'll notice here that a lot of this mirrors our discussion last week of steel. So for example, starting off with our advantages, we have that concrete has relatively high fire resistivity. That is, it doesn't weaken as much when subjected to high temperatures like steel did. And it's important to point out right away here that we have two basic types of concrete. We have normal weight concrete and we have lightweight concrete. Of course, there are a variety of other types of concrete. Of course, there are a near infinite amount of types of concrete based on the type of mix that is put together with all the different chemicals and admixtures and different types of aggregate, etc., etc. And each type of concrete will be a little bit unique depending on the needs of the project. But for this course, we're only going to focus on two types of concrete, this normal weight and lightweight. And the key difference here is, of course, in the density of the concrete. Normal weight is 145 pounds per cubic foot typically, and lightweight is around 110 pounds per cubic foot typically. And the key difference in terms of materiality of normal weight and lightweight is that lightweight will have more voids, more pockets of air in the concrete between the different pieces of aggregate in order to get it less dense. And so if we think from a thermodynamics perspective for just a minute and think about the insulative nature of materials, materials that have more air voids tend to be better insulators. And so it's lightweight concrete that will perform better for fire resistivity than normal weight concrete. And so to achieve a 2-hour fire rating with concrete for normal weight, we need a minimum of 4.5 inches. So that's the concrete above the flutes here of the deck in this structural steel example. And note that the deck here is typically going to be 2 inches. And so that gives us a total slab depth of 6.5 inches for a typical structural steel framing design. With lightweight, since it is a better insulator due to having more voids, we only need 3.25 inches minimum to achieve a 2-hour fire rating. And so that leads to an overall slab depth of 5.25 inches when we have structural steel framing. And if we achieve these two minimums, then that means we don't have to protect the deck. In other words, we would still need to spray fireproofing on this structural steel member here. But the concrete itself would be sufficient to provide a 2-hour fire rating between floors. And so we would not need to necessarily apply fireproofing to the deck. So when we have steel framing, these are the typical slab depths that you will see. 6.5 inches and 5.25 inches. Now let's look at a disadvantage. Again, mirroring what we saw last week, concrete has a lower strength to weight ratio than steel. And it also has 0 design tensile strength. That is, a concrete cylinder can take compressive force, but when we try to apply tension to that same cylinder, it will rupture almost immediately under very little force. So we can see that concrete actually has a lower density than steel, which was 490 pounds per cubic foot, However, it has significantly lower strength, typically around 4 to 5 kips per square inch, whereas our steel elements last week had a strength of around 50 kips per square inch, 10 times higher. And so even though concrete has less density, it has significantly less strength, and so it has a lower strength to weight ratio. Also, because concrete has zero design tensile strength, that means that we need steel rebar in any locations where there is going to be tensile forces. So, in a bending element, for example, where we have tension on the bottom face, that means that we are going to need at the bottom of the concrete beam. So to illustrate that again, we will have a compressive force at the top for a simply supported beam with a uniformly distributed load, and we will have tension on the bottom, and it's the steel rebar that will take that tension force. And a structural designer has a choice to make here when designing the steel rebar for this concrete beam. That is, they can over-reinforce the beam so that the steel is stronger than the concrete portion at the top, or they can design it as equal so that the tensile capacity of the steel is equal to the compressive capacity of the concrete, or they can under-reinforce the beam such that the steel tensile capacity is less than the concrete compressive capacity. And I'll give you a moment to think about whether the designer should over-reinforce, equally reinforce, or under-reinforce this beam. And as you think about that, think about this next disadvantage for concrete as a material. Recall that concrete is a very brittle material. That is, as you apply a compressive force to it, it will crack very suddenly with very little visible strain. Unlike steel, which was a much more ductile material and had more visible strain to it before it ruptured. So let's go back to thinking about the reinforcing of this beam. For a concrete beam, would it be beneficial to have the concrete or the steel fail first, or should they fail at the same time? Well, if the concrete fails first, that means that the failure of the beam will be very sudden and very abrupt, with very little warning, very little strain occurring. Whereas if the steel fails first, that means that there will be more visible strain in this concrete beam. There will be more visible deflection, more warning. And since having more warning is more desirable, we actually want the steel to fail before the concrete. And in order for that to happen, we need the beam to be under-reinforced. So typically, concrete beams are designed as under-reinforced, meaning that the tensile capacity provided by the steel rebar is less than the compressive capacity provided by the concrete. Now let's jump back to an advantage of structural concrete as a material. Concrete has high environmental resistivity after it has cured, and there's probably no better or more recognizable example or evidence of this than the Colosseum in Rome, which has stood for thousands of years. This high environmental resistivity also makes concrete ideal for foundations. The next advantage for concrete as a material is that it is typically more cost-efficient for vibration-controlled spaces. And this is because concrete has better natural viscous damping as well as larger mass. And you'll notice how some of these advantages and disadvantages sort of play into each other. So we started off by saying that the lower strength to weight ratio of concrete is a disadvantage because the project will end up using more material, but also that added material means that we have better vibration control. But again, since we have more mass, that also means that the foundation system will be affected, and we will need a larger foundation system, typically for a concrete building. Next, we have that concrete is able to form to nearly any shape. If you can create the formwork and pour the concrete in, you can create any kind of shape for your building. Now, another major characteristic of concrete that can't be classified as necessarily either an advantage or disadvantage, because it kind of leans into both, is that structural concrete is the only structural material that is actually formed on site. So steel sections, for example, are all formed and cast in a steel mill. Wood beams are all cut and sized at a wood mill. And also masonry blocks are all formed and cured at a separate facility. Structural concrete, though, is actually brought to the site as a wet mix, typically, and poured into the formwork, and it cures on site. So the advantage from that is that there is very little to no lead time when designing a concrete building. That is, you don't need to send the construction documents off to have shop drawings made and have the steel mill start to put together pieces for the project ahead of time with concrete. With concrete, all of your elements, your beams, girders, columns, slab, all of that is going to be made on site. And so all you need to do is let a concrete mix facility know what type of mix that you want so that they can bring it onto the site. And typically, as I said, that can be done with very little to no lead time. The mix plant will be able to put the mix together very quickly, so long as you don't have any special requirements in terms of admixtures or chemicals. The disadvantages to this system is, of course, that there are certain limitations and uncertainties involved. So for example, weather will have an effect on the curing process. Unlike with forming steel elements, which is done in a controlled facility or in a controlled environment, concrete elements are being cured out in the open. And so the outdoor temperature can have an effect on how these elements turn out. Also, when delivering a wet concrete mix to the site, there is a limited window of opportunity. And there's actually a maximum limitation for how long concrete can be in this truck before it arrives at the job site. And that limitation is typically around an hour and a half. If the concrete arrives to the job site any later than that, it will need to be thrown away. It cannot be used. So there's a lot more uncertainty involved with concrete because you don't know exactly how much it's going to cure in this truck on its way to the job site. And one way that we ensure that the concrete has not cured too much in transit is with slump tests. And a slump test is basically when we pour the wet concrete mix into a cone here after it arrives on site. We lift the cone and then we measure how far the concrete has slumped. And this will give us an indication of the water to cement ratio. Now, if you're thinking that that doesn't really sound like a terribly accurate test, then you're right. It's not. And so that's another disadvantage to concrete, is that there is some degree of uncertainty involved in what exactly you're getting on the job site. With structural steel, when we specify 50 kips per square inch steel, it's relatively easy for the steel mill to make that happen and be very accurate with hitting that number. With concrete, we have to be a lot more conservative to make sure we're hitting at least the minimum, and often what we end up getting on the job site is much higher than what we specified due to that conservatism that's required. So the curing process for concrete does take time. And in fact, to reach this design compressive strength, it will take typically about 28 days. Now, what happens if we place floor finishes over top of concrete that is still curing, that still has some moisture in it? Say we have some type of athletics facility, and we've poured our finish over top of concrete that's not fully cured. Well, now all of that moisture is trapped underneath the finish. And as the concrete continues to cure, it's going to try to escape, but it's going to be trapped by this floor finish. And so that will eventually cause warping in the floor finish. So when we use concrete, we have to be very aware of this curing process and the moisture that is in the concrete. Of course, this is all for cast-in-place concrete, but we also have precast concrete. So precast concrete is a lot more like steel. All of these elements are being cast and formed in a separate facility, and so we have better quality control, but the forms are limited. So now let's move on to another advantage. So concrete typically can achieve much shallower structural depths than steel, and we'll get into why that is in just a moment. A disadvantage, however, is that MEP integration can be tricky. So with steel design, all we had to do to accommodate this opening in the floor slab was provide 2 extra beams on either side. With concrete, it becomes a bit more tricky because we have this mat of reinforcement. And so placing an opening like this has a significant impact on the performance of this slab. And we will need to provide additional reinforcement all around that opening. Also, if you think about with steel, it would be very easy for us to design this bay without the opening and then come back in later to cut the opening and simply add these 2 elements. Those connections would be very easy to make either before the opening was made or after. However, with concrete, if we already had a mat with reinforcing completely across, to go back in and try to cut that opening through the existing reinforcing and then add reinforcing into concrete that is already cured would be a much more difficult process. And so concrete is not as easily reinforced post-construction due to its monolithic nature. And lastly, with concrete, we can accomplish relatively long spans with the use of pre-stressing. And we won't get into exactly what pre-stressing is in this course, but if you're curious, I'll post a video about it in the additional reading section. So that does it for the advantages and disadvantages of concrete as a material. And in the next video, we will get more into how to size different concrete elements.